All right, so we just got done, me and the dogs, pruning some trees. You always want to prune your trees, your fruit trees, in the cold time. And it's about 55, 50 degrees out right now in North Georgia. Good time to prune them. Might be a little bit late. Should have probably done that in December. But be that as it may, it's January. So I was just reading an article, mind my own business, not bother anybody. And I've been wanting to read this for a while, actually, to go over this. What is the top of the atmosphere? Now, there's lots of reasons you want to know the top of the atmosphere when it comes to climate change, when it comes to 66,000 miles per hour, all these various things. But this is I figured I'd share this with you because look, I just love Willis Eisenbach. It goes by Willie. I love this guy. Love what's up with that website, and any way I can promote, these guys, I will do it because it's fantastic. So we're just going to go over this. A lot of this is beyond my capacity. Oh, how dare you? How dare you talk about something you don't know anything about? Because I find it interesting. Crazy, right? Color me crazy. All right, so what is the top of the atmosphere? Pretty good question, no, especially when it comes to climate change, is it not? Yes, it is. In my last post entitled Avection, I was discussing the online mod train infrared light atmosphere model. So let's click on this. This is the, let's look down, locality, CO2 parts per million. Yeah. Oh, look at that, infrared light in the atmosphere. Man, look at that, it's just, locality, let's go, mid, I don't think I'm tropical. Let's go to mid altitude summer. It's 400 parts per million. So I'm not sure what all this is telling me, but it looks, oh, there we go. It looks pretty cool. This is the mod train, climatemodels.uchicago.edu mod train. Clouds, rain. Anyway, so let's read. I'm not sure what this is saying here, but that's pretty flipping. I love stuff like that. Once I figure it out. All right. A commenter pointed out in the past, I'd wondered about why the ModTran results show that the doubling of CO2 caused a clear sky, top of atmosphere decrease in upwelling long wave radiation of less than the canonical value of 3.7 watts per square meter per doubling of CO2. So let's go back to what he was saying. So all right, so we're going to go, we got altitude. So let's see what happens when we double water vapor scale, Freon scale, temperature. Oh, let's see, watts. Oh, right here. Okay, good. So we're going to double upward infrared heat flux, and we're going to double it. All right, so we got 260 watts per square meter. 260 watts per square meter. Let's double that, and let's see what happens. So we went from 400 parts per million CO2 to 800, and we had actually a little bit less watts per square meter. Ground temperature is 294 K, and I did a video on this a month or two ago, and off the top of my head, I can't remember what K was. It's I forgot, but I read this article in a paper. That was fantastic. Basically saying there's no tipping point, what the climatistas will tell you. So let's go back to, we got 294 is ground temperature. Let's go back to 400 and see what that says. That goes down, I imagine. Oh, 294.2. Huh. Doubling of CO2 parts per million. 290, yeah, it doesn't, why? Let's go to 1600. I don't get it. Why is it not changing the ground temperature? So I'm missing something. So let's just keep reading. But that's huh. All right. Anyway, so he says, I wonder why the Modtran showed a doubling of CO2 causing clear top of the atmosphere decrease in upswing long wave radiation of less than the 3.7 watts per square meter per doubling of TO2. So here's what he shows. So they're saying the canonical value of doubling of CO2 is 3.7 watts per square meter. But yet to figure out exactly why these values were so low, like, did that? I don't get it because that didn't. Maybe he's looking down. Maybe he's looking up. Does that change anything? Oh, okay. Down. Okay, here we go. So let's go back to 400 parts per. So it's 0.8086 watts per square meter. And we double it, 0.067. I'm confused. So what's this right here? Yeah, let's keep reading. All right, anyway. To figure out exactly why these values were so low, I went back to the paper, given the 3.7 watts per square meter value, new estimates of radiative forcing due to well-mixed greenhouse gases. I also recalled that in my earlier thread, commenters had mentioned that there were two top of the atmosphere definitions. One of them I'd use for figure 1 was looking down from 70 kilometers above the surface. All right, so 70, he's looking down 70 kilometers above surface, right there. 70 kilometers above surface, where was he? And the other definition was a tropopause. Upon rereading Murr and doing some further research, I confirmed that the measurements in the model results giving the canonical value of 3.7 watts per square meter doubling were taken not at the actual top, but at the troposphere, or tropopause. What the hell is a tropopause? So do we get... How do we do this? Yeah, that doesn't do me any good. It's way beyond my... Did he not? Maybe he did tropical atmosphere. And maybe he did 70 looking down. Oh, is that the tropopause right there? Ozone parts, I don't know what parts per, I'm not sure what B is. All right, anyway. The tropopause is the boundary between the troposphere and the stratosphere. It is a location where the temperature of the atmosphere stops getting colder with altitude. All right, it's the boundary between the tropopause is the boundary between the troposphere and the stratosphere, where the temperature of the atmosphere stops getting colder with altitude. The tropopause is at different altitudes at different times and locations. All right, so here we are at 70 kilometers. So which one is which? Let's just keep reading. It's interesting. All right. The Motrain model offers a graph of the atmospheric temperature profile of various locations. Here's a profile of what is called the U.S. standard atmosphere. And so this is the temperature profile of various locations. Right? So this is temperature in K. I don't think it's Kelvin. It was, I forgot what it was. But anyway, so the higher you get in altitude, the less the temperature is. So let's just assume this is ground. Yeah, this is ground temperature right here, 300 K. The higher you get in altitude, the less it gets to 197. That's about what, 15 kilometers, I guess? Is that, yeah, 15 kilometers. And then the higher you get after that, it gets warmer. And then it gets colder. It's just so interesting. All right, my calculations were done from 50 kilometers looking down, but as you can see at that location, tropopause is only at 11 kilometers right there. So here's a tropopause right there. All right, gotcha. So this is the tropopause right here. That is between the stratosphere and the troposphere. Is location or temperature of the atmosphere stops getting colder with altitude. All right, so that's a tropopause right there. It does change. Isn't that interesting? It does change. Huh. The tropopause at different altitudes at different times and locations. That's crazy. So what's this then cause? That's where it starts getting warmer, and then it starts getting colder again. All right. So I redid my Motron runs in figure 1, and this time measuring the appropriate tropopause levels at each location. You have to take two measurements when calculating long wave changes in the tropopause, one looking upwards and one looking downwards. All right, so let's look downwards. All right, let's look up now. Change the tropopause. Still right about there. Didn't change for me. Let's see. The final answer is the net of two changes, all right? With that as a prologue, here are my results. I've compared them to the results shown in Table 1 of the mirror paper. My average results calculated as in the mirror paper give a tropospheric clear sky increase in long wave absorption resulting from doubling the CO2 of 4.97 watts per square meter, extremely close to mirror paper. So he's got Table 1 figure of 5.04 watts per square meter per doubling is less than a 0.1 watts per square meter difference, and adding into the good agreement with a series figures known in my last post, he's giving me confidence in my trained model, okay? So are we saying that with a doubling, all right, so so what are we saying here? If we have if the sun is shining at 1100 watts per square meter, all right, on the earth, on the ground, on a cloud, no cloud cover right above us, is he saying that as the CO2 doubles, that will increase from 1100 watts to by basically 5.04 watts per square meter? I don't know. That's something that you might be interested in looking into. But let's keep reading. All right. There are a couple of surprising things about Figure 3, which is this right here. First, there's a slight reduction in the change for doubling of the absolute value of the atmospheric CO2 level increases. Unexpected. There's a slight reduction in the change per doubling. That's what I saw too. That's what I saw too. So we're going to go looking down. We went from 400 CO2 parts per million. And he said there's a slight reduction in the change per doubling of the absolute value of the atmospheric CO2 levels. So I went to 400, I went to 800. So 269 upward infrared, what is it called? IR, is it infrared? I don't think it's IR, I think it's called, whatever it's called. What does he call that again? I forgot. All right, but there's all right, so you go from 800 at 269.82 to 400. The change? Nothing changed there. Nothing changed. 269.82 to 1600. Yeah, all right, okay. 269.82. Let's go to 400. I'm confused. Go 1600. Yeah, well, yeah, look at that. That's good. I'm confused. All right, let's keep reading. Secondly, more importantly, I did not expect a large difference between measures taken at the two levels. The top of the atmosphere measurements average about 52% smaller than the tropopause measurements. This is interesting because of theory of why a CO2 increase leads to surface warming. The theory goes like this. The amount of atmospheric carbon dioxide is increasing. This absorbs more upwelling long-wave radiation, which leads to unbalanced radiation at the top of the atmosphere. This is a TOA balance between incoming sunlight, after some of the sunlight is reflected back to space, and outgoing long-wave radiation from the surface in the atmosphere. In order to restore the balance so that the incoming radiation equals outbound radiation, the surface must warm up until there's an additional upwelling long wave to restore the balance. So basically saying, hey, something's got to happen. The heat, something's got to give. We got to increase more heat to keep the balance. I point out the problem of this theory, which is that there are a number of other ways to restore the TOA to the balance, top in the atmosphere. Increased cloud cover or surface reflections can reduce the amount of incoming light. Increased absorption of sunlight by the atmospheric aerosols and clouds can lead to a greater upwelling long wave. Increase the number or duration of thunderstorms, more additional surface heat into the troposphere, moving it above some of the greenhouse gases and leading to increased upwelling to top atmosphere long wave. Increase the amount of energy evected from the tropics to the poles, increasing upwelling. A change in the fraction of the atmosphere radiation going upwards versus downwards can lead to increased upwelling radiation too. So there's no requirement that surface temperature increase in response to increasing CO2. Did you hear that? There is no requirement that surface temperatures need to increase because of increase in CO2. There's other ways to maintain the balance. With as a prologue, the insight for me is from the big difference between TOA and troposphere measurements, as I've been thinking about the imbalance at the actual top of the atmosphere from doubling of CO2 would be 3.7 watts per square meter. But in fact, it's only about half that. Now, as I pointed out above, there are a variety of ways that TOA radiation can be restored. So how much is it from surface warming? Well, here's the relationship between surface warming and the upwelling TOA long wave. And this is a little bit beyond my capacity here. I just find it interesting. As you might expect, over much of the planet as the surface warms, the upwelling TOA long wave increases. This makes sense. A warmer surface radiates more long waves, so you think there'd be increasing upwelling top of atmosphere long wave. But at temperatures above 26 Celsius, the situation changes rapidly. Above that temperature, the upwelling top atmosphere long wave drops very rapidly with increasing temperatures. It drops very rapidly with increasing temperature. That's altitude, but look, I'm not an expert at this. It's just interesting to me. Why does the temperature go down as you're getting higher altitude, where it goes up right here? Like, what causes that right there? Something happened. I don't know. I just find it incredibly interesting. I ascribe this to the actual tropical thunder. Let's see. But temperature above 26 Celsius, the situation changes rapidly. Above that temperature, the upwelling top atmosphere long wave drops very rapidly with increasing temperature. I ascribe this to tropical thunderstorms. These form preferentially at temperatures above 26 degrees Celsius. All right, so, and all this is way beyond me. Other things being equal, according to series data, a 1% Celsius increase in global output temperatures leads to a 1.9 watt per square meter increase in upwelling top atmosphere long waves, which by what is clear coincidence is a fair amount of the decrease is the amount of the decrease in upwelling TOA, which would result from the doubling of CO2. It's worth noting this in context because we're dealing with radiation in the atmosphere. Things happen at the speed of light. A cross-correlation analysis shows that there's no delay between monthly changes in surface temperatures and monthly changes in TOA long wave. All right, so I'm going to an analysis such as this one is generally useful to keep in mind what I modestly call Willis's first rule of climate. In climate, everything is connected to everything else, which in turn is connected to everything else except when it isn't. I can defend my own words, but not your interpretation of my words. When you comment, please quote the exact words that you are discussing exactly. So why is the surface warming faster than the CO2 increase would suggest? Well, the main reason is increase the amount of sunlight absorbed by the surface. The solar energy has increased by 1.5 watts per square meter over the 21 period of the series record. Okay, the main reason is the increased amount of sunlight being absorbed by the surface. Sounds like because of cutting down trees, but we have more green cover now. I don't think asphalt's not a good thing. Anyway, we just got lots of freaking smart guys quoting in here, man. Here's Donahue, maybe useful to help and explain the counterintuitive increases. This whole thing, these guys are well beyond me, but I love this stuff. And you should too, it's interesting. Because you're sitting there thinking, why? Just go back to this. Why? I mean, there's a troposphere. So as you go altitude, it reduces the temperature until you get a certain level, and then it goes up. Why? Then it goes down again. Air pressure? I don't know. It's interesting. All right. Love your thoughts. See ya.